I want to give you one more example of a related rates problem. I'm going to do this one with an angle. You don't have this question, so copy this down. A rocket is taking off vertically at a distance of 600 meters from an observer. At a distance of 600 meters from an observer. If when the angle of elevation is pi by 3 radians, it is changing at a rate of 0.5 radians per second, how fast is the rocket ascending? Okay, so let's just draw a quick little sketch of this. So we've got a rocket that's taking off vertically. So here's my rocket ship heading up, and it's at a distance of 600 meters from an observer. So here's the rocket launch pad, and 600 meters away, here is the observer. Okay, so rocket is taking off vertically at a distance of 600 meters from an observer if when the angle of elevation is pi by 3 radians. Okay, so angle of elevation means this. We're looking at this rocket, and if it's here, this is my angle of elevation, and as it goes up, you can see that angle of elevation increases. So I'm just going to draw one, for example. So here is my angle. I'm just going to label it theta, my angle of elevation. Here's my rocket ship, and then we can see that that angle keeps on changing. In fact, it tells us the rate at which it changes. Okay, so if when the angle of elevation is pi by 3 radians, it's changing at a rate of 0.5 radians per second, the question is, how fast is the rocket ascending? And it's kind of cool that you could be an observer, and if you were a cameraman and you were trying to keep this rocket in your sight, then you would have to keep on adjusting your camera as that rocket went up to keep that rocket in your sight. And just by looking at the rate at which your camera angle changes as that rocket goes up, you can know how fast how fast that rocket is moving. Okay, so the whole key here, though, is that we can find a relationship between what we know, which is how fast the angle of elevation is changing, and how fast that rocket is going up. Okay, so let's just start off by listing our variables. Let's, of course, let theta equal our angle of elevation. And what else do we have here? I guess we've got, I'm going to call this y. I'm going to let y equal the height of the rocket. Okay, so if y is the height of the rocket, then y keeps changing as well. So what is it that this question is asking us to find? How fast is the rocket going up? Well, then what we're actually looking for is what is that velocity of the rocket? What is the change in y with respect to time? Distance over time, velocity. And what is it that we're given? So here is what we're given. We are given that the change in theta with respect to time is equal to 0.5 radians per second. We're asked to find dy by dt when theta is equal to 0. No, when theta is equal to pi by 3. Sorry, mixing up a rate with an actual measurement. Who does that? Okay, so then what's our relationship? And here's something we haven't done before. Our relationship between the angle and the opposite side when I know the adjacent side is this. The tangent of this angle theta is opposite over adjacent. So that's the equation that I'm going to use to find my relationship between theta, d theta by dt, and dy by dt. Let's simplify it before we start. 600 tan theta is equal to y. Then taking the derivative of both sides with respect to time, note I've got a variable here and a variable here. A variable theta, that angle keeps changing. A variable y, that height keeps changing. And I'm taking the derivative with respect to the third variable, time, which means this is implicit differentiation. So take the constant out front. The derivative of tan theta is secant squared theta. The derivative of the inside function is d theta by dt is equal to the derivative of y with respect to time. So this becomes 600 times secant squared d theta by dt is going to give me dy by dt. And why didn't I put this in here? Well, because I guess I'm going to calculate it first. If the angle is pi by 3, then the cos at pi by 3 would be, at pi by 3, the cos would be 1/2, which tells me that the secant at pi by 3 would be this reciprocal 2. So I need to put in a secant squared. So 2 squared 4 times 600 times 1/2 is going to give me 1200 meters per second. Is going to give me my dy by dt. Don't tell Don't tell your physics teacher that I didn't put units all the way through this. It's going to drive her crazy. Anyways, I hope that helps you with your angle questions. I'm going to put one more up here just for you to take a picture of and have a look at. It's a little bit different, and it might help you with some of those related rates homeworks questions. So here's the second one. So I know you know how to pause this and do it again. And I'll flip it over and give you a picture of two more. Why don't we do it one at a time? Okay, so you can have a look at that one with a ladder resting on a vertical wall and sliding down the wall, and you're looking for how the angle changes. And probably this one here is going to help you quite a bit. Be sure that you are always working in radians mode.